I want to look for a short lecture and a little bit longer one next time about building simple polygonal models that we're going to use throughout the class. And I have a lot of demos. You've probably seen some of them. I've shown some where we use a cube as our model. But even with something as simple as a cube, we want to have a data structure for representing it. And so in this lecture, I want to introduce the notion of vertex lists and edge lists and a little bit deeper idea of trying to separate what we call the topology from the geometry, and I'll define those terms. So we'll look at that in this lecture. Next lecture, we'll actually look at the code for doing a rotating cube, and then in a couple of more lectures after we talk some about viewing, I'll come back and talk about mesh structures in particular, because meshes are what we use all the time in CAD and other types of applications. So let's start with a simple mesh. Maybe not that simple, because what it has is something that our simple examples so far haven't had, in that this mesh has a lot of edges which are shared between multiple polygons. It has vertices that are shared by many polygons, and the polygons themselves are not all of the same type. Well, some of them have 4 vertices, some of them have 3 vertices, as there might be a 5 vertex one in there. There's certainly a vertex in the middle there that's shared by a lot of polygons. So we can say, well, here's a mesh. What is it? It's something that consists of 8 nodes, and if you count them up, there's 12 edges in there. And notice that I've drawn that, and this is how we get to this idea of topology, is I can draw that without really talking about where those vertices are located. And in fact, even if I try and move a vertex a little bit, I'm not going to change the basic connectivity that's expressed in the topology. Now also we can distinguish between interior and exterior polygons, because you might say, wait a minute, if I go all around the outside, that's a polygon, isn't it? And that's true. So what we're usually concerned with are interior polygons, polygons that have no other polygons inside of them. And notice also this has no edges crossing each other, so it's a reasonable kind of structure. We also used to, not as important now, but I'll point this out why it's a potential issue, is that we have edges which are called interior edges, which are shared, and exterior edges which only belong to a single polygon. Now ultimately, each of the vertices or nodes in this mesh are going to have a geometric location, and let's assume this is all in 3D, so they each have an X, Y, and Z. So you say, okay, well, how am I going to represent that? Or even simpler, how am I simply going to display it if I have all of this vertex information? Well, the simplest thing you can try and do is simply push each vertex onto an array, and then you'll eventually send this vertex array out to the GPU. So I can use, here's a nice way of using the push function that's built into the array, instead of using indexing, and just says, okay, add this vec3 of x, y, and z for vertex 1. You were referring to, let's see, 1, 6, and 7, which is this one over, where's it, 1, 6, and where does 7 go? Vertex 7, 7, come on, I'm missing it someplace here. Oh, it's this one here, right here. I'm pushing this one onto an array, which then I'll eventually send out to the GPU to display, and every time I push something on, I'm increasing the length by 1, so I know how many, in the end, how many vertices I want to display. Although I have to be a little careful here, because each one has a different number of vertices in it potentially. But the thing I don't like about this is it's pretty unstructured. And if you consider something like this, like suppose when I'm having this in an interactive application, and what I can do is point my mouse to a vertex and actually drag it to a new location. And you can see the potential difficulty here. If I take this vertex, which is the most dramatic one, it's shared by 4 polygons. And so if I move it, then each of these 4 polygons will be displayed differently because of the different geometry. Now, if I use this kind of idea of pushing everything into a single array, then what I have to do is if I move that vertex, and what number was that vertex? It was vertex 7. If I move vertex 7, that says I'm going to have to now search that entire array for all the occurrences of x7, y7, z7, and change all of them. And if this is a really big structure with tens of thousands of polygons, that's clearly really an inefficient way to do it. So I have to worry about that problem, and the answer to this, like many computer science questions, is, oh, you didn't build a decent data structure, and that's what we're going to do, is build a decent data structure. Now, one other thing I want to be careful with here is if I go back and I look at that polygon, the order of the vertices in some sense didn't matter. So if I ordered the vertices v1, v6, v7, everything was, that's one way of doing it. But I could have started with 6, then gone to 7, and back to 1. But I want to claim that v1, v7, v6 is different because you're encircling the polygon in a different direction. So if you look at it here, if I go v1, v7, v6, where did v6 go? I guess I'm really talking about, let's look at v1, v7, v2. If I circle it this way, then this is a clockwise direction when I'm pointing, looking at it from the outside. But if I go v1, v2, v7, I'm encircling it in a counterclockwise way when I look from the outside. On the other hand, I say that v7, v2, v1 is the same as v1, v7, v2 because both of them encircle it when in a clockwise way looked at from, we're assuming we're looking at it from the outside. So that gives us the notion of inward and outward pointing faces. Every polygon has 2 sides, and I want to make sure that, I want to make sure I render things in a consistent way because I have the potential in all versions of OpenGL of coloring or even not rendering the outward or the inward face. And if an object is not, if an object is convex, you'll only see the outward, the outward pointing faces. If it's not convex, then you may see some of the inside faces. So consider, for example, a cube. That's a convex object, and we don't know what the colors are on the inside. However, if I take off one of those faces, now you can look inside, and the colors of those inner faces may be different from the colors of the outward faces. So I want to be able to distinguish between the two. So the convention is the right-hand rule, that if you think of the normal pointing out of a face, so that's the outward face, and I hold it with my right hand, that I encircle it in a counterclockwise way, which is the direction that the fingers on my right hand would be pointing. So we would want to have 0, 3, 2, 1, or 1, 0, 3, 2, or 2, 1, 0, 3, and any other order would correspond to an inward face where the normal would point in the opposite direction. And so we'll be able, if we need to distinguish between those 2 faces. Now let me get back to this geometry versus topology issue. The geometry is where things are located, because where are these vertices in space? The topology is really about how they're organized in terms of vertices and edges. So if I take, for example, a triangle, it's something that has 3 vertices and 3 edges, and they're connected, and where those vertices are actually located really doesn't matter in terms of what can I say about this triangle. That fact that it is a triangle, the fact that I have certain theorems I can say about a triangle. So we can say that when we say that a polygon is an ordered list of vertices connected by edges, that says nothing about their geometry. And if I'm careful and I don't move things too much, as in when I showed you moving a vertex in that mesh that we started with, I don't really change that structure. I still say that vertex 1 is, let me go back to that. If I move this, I still have the same topological relationships. Let's look at edge 1, it connects v1 and v6. That doesn't change if I move one of these vertices a little bit. Obviously, if I move it a lot, I could really screw up the topology or what happens if they're on top of each other. But we're not going to worry about those issues. The basic structure about how edges and vertices are related doesn't change when I change the geometry a little bit. And that's what we mean by the topology. Now, one of the advantages of that is that if I change the geometry, I can actually do that very, very efficiently because if the topology does not change. So here, let me give you an example of that, and this is the way we'll probably do things most of the time. Instead of using the geometric locations of the vertices, what I'm going to do is have pointers to the to where the vertices are located. So if you think of this in terms of pointers, then this all makes sense from all your programming experience. But notice if you look at it this way and say, well, look, I have 5 polygons, interior polygons in that mesh. The first one has vertices v1, v7, v6, and likewise the second one has vertices v8, v5, v6. That's describing the topology right there. The vertices will point into a single list of where the vertices are actually located. So v1 will point to the geometric location of x1, y1, z1, and likewise v7 points down here, and so on, and you could fill out the rest of this. So I've done what I said I wanted to do, which was to separate the topology from the geometry. Now if I interactively change a vertex, it's really not affecting anything here, and each vertex, its geometric location, only appears once, so I have a much more efficient way of doing that. And you're going to see that's the way we're actually going to wind up writing most of our code, and you won't even be thinking about it. But there's a potential issue with this, and it's following. You say, okay, draw the mesh. Well, what do? I come over to the first polygon. It says, oh, draw these vertices. Here's their locations. Draw the second one. So it's organized in terms of polygons. Polygons point to vertices. Vertices point to the geometry for each vertex. One problem that used to be a more serious problem when you had CRT calligraphic displays was that you drew all the interior edges were actually drawn twice. So when I drew this one, I went in this direction, and when I drew this one over here on the left, I went in this direction. Well, look what's happening. Because of the shared edge, it's drawn twice, and because as you went through this list to display over and over again on your CRT, what would happen is that these interior edges would appear brighter than the outside edges because they were being drawn twice. Well, in a raster system, this is not an issue, although you can argue that you're wasting a lot of time drawing these extra edges, which may or may not be true in a GPU-dominated system. But let's look at another way of looking at that, at the whole modeling, which says, well, what if I modeled things by edges? Then I could say just draw edge 1, edge 2, edge 3, and they'll only be drawn once. So let's look at a little model for doing that. So here, if I list the edges for that same example, each edge connects a pair of vertices. So edge 1 connects vertex 1 and vertex 6. They'll again point it into the where the actual edges are located. So once more, we've separated the topology. We've just decided to put the topology in a slightly different form and a slightly different data structure, and the geometry is still separate. But here's the issue, that what happened to polygons? Where's the notion of polygon 1, polygon 2, polygon 3? If this is just being drawn by lines as a wireframe, it may not matter to you much. But if it's in an application where you're doing shading and you really need to know, or you're filling the polygons, so you really need to know what is polygon 1 because I'm going to fill polygon 1, and what's polygon 2. You've lost that structure. So the edge list has something going for it, but is something lacking. And it turns out if you look at sophisticated CAD modeling programs, they will have very complex data structures in them, which will have multiple representations of meshes and other objects. So it will be represented by edges. It will also be represented by a vertex list, so you can choose which representation works best for whatever you're trying to do with that object. Now, to get ready for the next lecture, let me say what we're going to do in the next lecture is say, okay, let's take a particular structure, which is a cube, and now we're saying, well, I know I should talk about vertices and number them because vertices will point to geometry. So here's a cube, we're going to call it the color cube because I'm going to color each face differently, but I'm going to express it in terms of the quadrilaterals, the 6 quadrilaterals that form the cube, and I'm going to express each of those in terms of 4 vertices that are numbered. So, for example, quad, and I'm going to have a quad function which will actually do some more, and we'll see that in the next lecture. So one of them, quad 0, 3, 2, 1, 0, 3, 2, 1, that's this one in the front. And notice the order obeys the right-handed rule. I go 0, 3, 2, 1. By the right-hand rule, I encircle it in this way, and I'm going around it counterclockwise, and the normal points outward this way. And you could check that it's true for the other 6. But this will be the starting point for our next lecture.